Pleased to introduce our next speaker, Erik Arakelyan. Erik is a senior researcher at NVIDIA and is going to talk about LLM compression. Stage is yours.
Thank you very much. So, hi everyone, I'm Erik, and today we're going to talk about compressing LLMs, the good, the bad, and the ugly side of everything of that. So we're just briefly going to say, like, why do we need to compress LLMs, what to compress there, and we're going to run into like different families of compressions. And at the very tail end, speak about something more novel, like a novel way to do KV cache compression, which will explain what it is. So I think I'd rather not stand here. I'll try to stand here. Great idea. Okay, stuck on them. So, first of all, like we know that LLMs we're getting more and more usage out of LLMs. More people are using LLMs, and people are using LLMs more. So more tokens per person and more people overall. And we know that training LLMs is very costly. Approximately like every 8 months, the cost of training the latest, greatest LLM doubles. However, with all this considered, LLM inference costs are deflating, which is very nice, which is partly due to the amount of technology that we're going to talk about now. So, and we kind of want to have LLMs accessible to more people, for more people on consumer use even. That's why we have a very big need to compress LLMs. Compress them so that it's accessible. So, why is it hard? It actually boils down to one very, very simple thing. Attention is quadratic. We will explain what that means later, but attention is quadratic in terms of the sequence length. And as the sequence lengths get bigger, it usually dominates most of the inference. That's why it's the biggest bottleneck, one of the bigger bottlenecks of serving LLMs. So we'll start talking about sparse attention and how to compress attention. So first of all, we have to define two things, what is pre-filling and what is decoding. So all of your prompt that is static, you just feed it to the model, it is called pre-filling. You just like statically fill it, you can't circumvent the cost of the attention. And everything in decoding is like different, you just like decode one token at a time or several tokens at a time if you're feeling lucky, and just go from there. And the idea is that we need to look at into two metrics, like time to first token, essentially how much did it took to pre-fill and get the first token, and at every iteration step, at every decoding step, what's the inference cost? So let's start by talking about how to compress attention. So the things that we're going to talk about during this talk is what is sparse attention, how did we come to the ideas, what are the best ideas there, what questions have been answered and what haven't. We're going to say what are like internal memory components that are used outside of LLM or internally fused into the LLM. We're going to briefly skim over approximations of softmax and why softmax is a computationally hard operation. We're going to talk about learnable decompositions, and we're not really going to talk about quantization and attention distillation in terms of time because we still have a lot of slides to get through, so sorry on this one. So, sparse transformer. This was like the original novel work that said, okay, we know that attention is quadratic. We have every token has to look at every token. Why don't we break this paradigm? Why don't we, instead of looking at all the tokens, look only at some tokens? So you can see several attention patterns in between here. One is called like sparse transformer strided. One is called sparse transformer fixed. The idea is that the initial work just decided to fix these patterns. They said, we just think this is a natural way to represent our data. They were working on images. We know that in images there's like this locality of features that is more important rather than the global attention in of itself. That's why they decided to just experiment with a couple of patterns and see what's going to happen there. More mathematically correctly, we can say that a self-attention layer maps a matrix of input embeddings X given a pattern S. So per head, we can have different patterns. That's what was interesting about it. And the essence of the idea is that the initial attempt said, what if my head, instead of attending, or if instead of having all tokens attend to all tokens, chooses the square root amount of tokens and attends to them. So attention goes from n times n to n times square root of n. That's like already like one magnitude of computation that we connect less. So this is what I was talking about. We essentially just say, yeah, let's have one head just look at previous L positions, and the other head attend over ELF location. So you see that light bluish things. I hope really it's visible. That light bluish thing is essentially the second head attending the ELF token in of itself. This concept would later be known as verticals and slashes, but we'll reach that a bit later. So, and the other thing was that there is a need at times to compress information within the LLM, within the LLM inference. Essentially saying that because softmax usually cannot zero out a probability or an attention score, we usually get some type of a signal. At times, we don't really need that noise. So there are tokens that need to have more attention pulled into them rather than across different layers. This concept is known as attention sinks. You can see that there's like vertical, like big lines, meaning that they attend to every token that came before it. This is known as attention sinking, but attention sinks usually occur naturally after training. However, in this case, they just decided to handcraft it and put it as an attention pattern. So, softmax function, as I told you, prevents all attended tokens from having zero values. This requires aggregating some information from other tokens across all heads in all layers, even if the current embedding has sufficient self-contained information. So we just need to compress at times what the LLM goes through. So after this, there have been many variations of what type of patterns are better, what types of patterns are worse. One of the more popular ideas around this field is called streaming LLMs. It came out in 2024. It said, let's actually look at the very first token known as start of the sequence or CLS token. Naturally occurringly, a lot of attention is pulled into it. In a lot of embedding, like prior to 2021-ish, research actually used the first token as the average token of the sentence. So they said, okay, why not use that strided attention concept? Just add one very fixed attention pattern to the first token. So everyone looks at the first token and the L tokens behind them. And this worked very well. This is computationally much faster than doing it in n squared. So we have just multiplication of sequence length multiplied by the window. And this is a precursor towards ideas of strided window attentions, strided complete window attention, and stuff like that. But we're not here to speak about banalities of what type of patterns are there. There has been a much more interesting work that said, let's answer several questions. Do changing patterns, what type of patterns work? Because more or less we don't really know. We didn't up until this point know. There wasn't a very granular evaluation of this type of methods. There wasn't an understanding of what works, what are the general things that give you benefit, what are the general things that are bad to do. So in this paper that came this year that's called Sparse Frontier, they decided to say, okay, let's essentially divulge all this field into different type of paradigms, create 9 data sets, 9 evaluations of different variety, ranging from needle in a haystack, essentially just retrieval, to more hard tasks like summarization. They have 9 tasks of different fidelity, of different variety that they started to test on. And so they said, we essentially surveyed the field and found 4 axes that are overlapping in between all the papers that came out regarding sparse attention recently. One is the unit of sparsification. Essentially, what type of pattern do you get to? Do you get verticals? Do you get slashes? Do you get blocks? We'll talk about that a bit later. Importance estimation, which is my attention pattern dependent on the content, or is it used across all of the inputs? budget allocation, are we doing uniformly essentially the same compression per layer, or are we kind of adjusting that? That's actually one thing that we're going to address a bit later on. And then KV cache management, this will be talked in later. So, and yeah, as I said, there are diverse task types from retrieval to multi-hop tracking. The tasks are both natural and synthetic, so we have a big variety to test upon. And just to talk about what units of sparsification are, like downwards you can see like all the plethora of research that came in between this. Like we can see star attention, log sparse, threaded. We're not going to talk about benefits and outweights of each one. We're just going to say what works in between all. So main difference is the structural units of attention matrix. Essentially, how do we construct that patterns? And that can be divulged into vertical columns, slashes, and blocks, like separate blocks. Indeed, one very interesting inference way, which is called M-inference, uses all of these ideas in a combined way. So they essentially define a dynamic search process during their pre-fill phase. They say, let's understand what type of an attention pattern should each head have. And the loss there is very simple. They say, let's give this head all the possible attention patterns with some hyperparameter search, and say which one gives the closest result to the original attention. Just very greedy search, very like refined way to do this. And yeah, like subject to some budget, and the budget here is how many floating point operations you can do. Like they have to be equivalent in that regard. We can't just say, yeah, like just don't sparsify it, just use something very similar to full attention. And the idea is that this method actually works. It gave much better results at the time than like your favorite optimization methods used from for every type of fast inference. So it's much faster because it dynamically per iteration decides what type of pattern should a head use, and during the decoding step, it essentially unrolls what type of parameters should each head have. Should each head have, yeah. So meaning that we essentially construct our patterns depending on the data. But like returning back to essentially what we're talking about, how to like understand all of this in a more refined way. Let's talk a bit about block-based methods. Those are select blocks of units to approximate full attention. Like we saw in star attention, we just like pick blocks and either average over it or maximize over it or somehow aggregate over it. Like M-inference actually uses block sparse attention additionally to their dynamic setup. The vertical and slash patterns, they're very simple. Essentially, they say how many attention sinks do we want to create, plus how many tokens I'm confident at looking back into. So usually, like several things like tri-shape and M-inference that we talked about came around and said, yeah, districts generally work, but how much? So regarding importance estimation, we have like another set of researches like streaming LLM, LM infinite, and MOA that says that essentially determines the number of initial tokens that need to be used as attention sinks. Because we don't always need to have like the first CLS token, it might be the first CLS token plus 2, plus 3. We don't really know how much, but that can be dynamically inferred from data, that can be searched over data. And yeah, content-aware methods typically estimate the importance of Q and K units. Essentially, what's their dot product or what's their dot product distribution is supposed to look like at least. So budget allocation is very simple. We either do it uniformly. We just say every head is the same, just compress similarly. Or like novel methods like pyramid KV, pyramid infer, and what we're going to talk about in our KV cache segment, essentially say that this can be inferred dynamically or even learned. I said no learnable budgeting scheme. I lied kind of a bit. There is already one. So let's say the findings or what questions did they answer. So given a fixed computational budget, should one choose a small model with denser attention or bigger model with sparser attention? This seems like a very trivial question to people who actually did empirical studies, because the answer usually is the bigger the better. But there is actually theory behind it. So they essentially said, let's compute the performance, that's the y-axis, along the number log scaled of the flops. And we see that the models have different scales. They used Qwen 2.5 of 7B, 14B, 32B, and 72B. And essentially what they found out is that on smaller sequence lengths, all the models usually are on a Pareto frontier, meaning that there is no overlap in between bigger sparse model and smaller dense model. So usually just increasing model size for smaller sequences is better, because even with high compression. However, the same thing cannot be said for longer sequences. Whenever we have longer sequences, now we start to have overlaps. So we can have cases where a bigger sparse model is not sizably, but closely worse than a smaller dense model. And usually, like, the Pareto frontier argument in this case breaks. So efficiency crossover where large sparse models surpass smaller dense ones from the same computational budget. We see that type of a phenomenon. For prefilling, models with 5 to 15 compression ratios remain optimal, while those with 20 compression fall behind optimality boundary. So there is a clear cutoff rate on how much can we compress before the model actually is not flop efficient anymore. There is like an explicit number, and it can be found per an architecture. So the second question is, what is the highest achievable sparsity that guarantees performance is preserved? They essentially said that for sequence lengths that are small, for 32,000 like tokens, there is no strong correlation. So essentially, everything can be compressed as much as they want, and they will still get a model that does not really degrade in its performance compared to the original model, which is very interesting. However, the same cannot be said for longer sequences. Again, and in order to understand it, they performed the one-tailed Welch t-test, essentially on the dense model and its sparse counterpart, and said across each combination of model size and sequence length, if the performance is statistically significantly the same, then we're good. If it's not, then yeah, the model should be discarded. So for prefilling with vertical slash, no clear correlation. As I told you, across all sequences, essentially everyone can be compressed as much as we want, almost to no avail. For decoding results, we're explicitly differentiating between these two modes because they differ. Like, prefilling is harder usually, but decoding, you can use more tricks during decoding. So model size emerges as the critical factor again. In fact, 7B model exhibits high variability and a clear negative correlation between sequence length and maximum compression. So in this case, we need to have the models that are bigger. Large models maintain consistently high compression radios regardless of sequence length. So essentially, it's easier to compress them because they have more information ingrained into them, and that's why we can sparsify the information flow. So there is like a question, is there a one-size-fits-all method? Like, can we literally just say, always use this method, it is going to guarantee? The short answer would be absolutely not, definitely no. So they essentially said, let's use during the prefilling different types of prefilling, like block sparse, flex prefill, which is an adaptive prefilling way, or just like vertical slashing. And during their decoding phase, they used KV caching, which we'll explain what is later on, and different type of decoding architectures. And what they came up with is that performance for retrieval task, this is very task dependent, by the way. For retrieval task, it turns out that the severity of degradation correlates directly with the number of queries. So by number of queries, we mean for a needle in a haystack, it asks essentially, give me one key from like long context before this. But as the task gets harder, so for example, if we have 16 keys, like find me 16 keys from before, the performance starts to degrade. And uh, they don't really explain why this happens, but it's there is a clear trend that this is a phenomenon that it happens across all model varieties, all model fidelities. For block-level units of sparsification, we observe contrasting behavior between prefilling and decoding. So prefilling performs poorly on multi-query retrieval tasks. This is very natural because we essentially aggregate a token information that we might need to recall later. So essentially, we might not be able to reconstruct the token anymore. This is very natural because for block sparse attention, we essentially aggregate several tokens together. We merge them. However, for different type of tasks like summarization, it's actually quite good. It actually is computationally efficient, and it's better to do it that way. Second, block sparse selects continuous blocks of key tokens rather than individual tokens, as I told you. And yeah, that's why it introduces redundancy. So, performance on tasks with high scope and high dispersion, like story filtering, multi-hop reasoning. These are tasks that are more natural, and they don't require retrieval. They require some type of a information processing, information latent finding, and information descriptor orientation in a way. So chunk-level methods like block sparse quest consistently match or outperform token-level global selection methods. In this case, it's very good because we need to understand on average how, like for summarization is literally aggregating the information of data. That's why having an aggregate block method is helpful. So results stem from the fundamental differences in how information must be processed. While attention distributions for retrieval tasks are connected on local windows, for tasks that have different dispersion, they're definitely not local. They need to be more global and refined. So the last question is, can we establish scaling laws for sparse attention, which can generalize to larger model sizes, sequence lengths, and compression ratios? The answer is very much yes. Quite surprisingly. So they used the same power log linear scaling law, and they said, let's just fit an R squared into this. And it turns out this was able to explain the incoming data quite well. They essentially said, let's not use the biggest compression ratio, biggest context length, and the biggest model, and see if the model is able to, if our model is able to predict it. And it was able to quite convincingly predict it, upwards of 80% of R squared, well, which is very nice for us. So, we are able to say that there definitely exists scaling laws for sparsification. So, one thing that I didn't talk about yet is that all of these patterns, they have not been learned. They have been patterns that we set priorly or dynamic research over. But patterns can also be learned. One big work about this is reformer. So they say that attention term Q multiplied by KT is problematic. And the reason for this is that there is a shape B on length on length. So when we multiply this, we might have, if our sequence length is 64K, we might have a matrix that needs to be 64K on 64K, which is 18 gigabytes of VRAM memory. That's not very nice. So that they said, what if we set two tensors, Q and K, to be equal, and we're interested into understanding how this softmax Q KT is multiplied. And for this, they did a very neat trick. They said, what if we learn a hashing function, not learn, create a hashing function that given an input, essentially clusters similar points together. That's known as local sensitivity hashing. And we're not going to essentially dive into why it works statistically, but the idea is very simple. We just say, project your data into a lower dimensional space with a random projection, actually a random Gaussian projection, and you'll be fine. And that hashing works. So for a depiction of what it means, in more scale, essentially we project it onto a lower dimensional space and divide the space into several parts. And now those several parts become eventually our clusters that we're going to use during decoding. So how does that happen? We essentially say that queries are equal to keys. And on the right, you can see what normal attention is and what bucketed attention like this is. After that, we do local sensitivity hashing bucketing. So we essentially query tokens together. And then only we do the rest of the inference. So like we sort them, we chunk sort it, and each bucket attends only to the other elements in that bucket. They also use several tricks, like saying that all the buckets also have to somehow attend in between each other, at least like within one component. So they also create artificial attention sinks. They say like, yeah, this token has to be the connecting factor between these several local sensitivity hashes. And because local sensitivity hashing is a logarithmic operation, our attention becomes from n squared into n log n. So it went from n into n times square root of n into n log n. Now let's do even better. So let's talk about attention with low rank decomposition. We're going to talk a bit about linformer. So linformer is a very, very simple idea. They say, let's say we have like our usual attention multiplication, let's name it P, like the way we get attention. And they say, we essentially took a look at how this attention matrices behave. What do we mean by that? They say that they looked at different heads. They plot the normalized singular value decomposition and their singular values over 10K sentences. And then what came out is that the results exhibit a clear long-tail spectrum distribution across each layer, head, and task. Most of the information of matrix P can be recovered from the first largest singular values. This is like 2020. Now the trend is not as clear, but still like something similar happens. So just to tell you what was happening is like the first 128 out of 512 singular values are able to explain like 90-something% of variance in the data. How are we doing on time, by the way, guys? Yeah, okay. So because this is true, they said, okay, then why not do a simple decomposition with two matrices? Like we can decompose attention with two matrices. And it's very, very simple. They say, what if like the K and V matrices, like we project them into a lower dimensional space, and then only then we compute the attention, so in the lower dimensional space. And because we fixed the parameter for how low the low dimensional space should be, like we've fixed some random K, our attentions becomes linear. It becomes big O n times K, given that K is a fixed number, it becomes big O of n. So the mathematical derivation of everything should be here. So now let's talk about what if we add memory into LLM components. So what if we retrofit transformers with a separate memory module, something that can either learn to compress memory from the attention heads, from the tokens, or something that can be externally added, which is the second part. So the idea is to map past hidden activations to a smaller set of compressed representations. Essentially, we don't want to forget the tokens that we do not necessarily attend to. Our attention can be sparse, but we might need to have some type of an external data structure to keep our compressed memory. So the compressive transformer essentially was a pioneering work in this area. They said, okay, let's divide our input into several chunks, into several window chunks. And for each new chunk, we have like a LIFO, like last in, first out data structure. We fill it in. Once it's filled in, the new element that we want to input, we have to evict some information that's prior there. Instead of evicting, we take that information and we compress it using some mean pooling or like some very basic function. And we put it into another last in, first out data structure that is attended to with the original one as well. So this is like a better depiction of that. So after some point, we start to put all of our token information into previous element. This is essentially one of the precursor ideas to what KV caching was, to why it was created. And there is actually like something known as memory transformer. The person that created this is doing a talk like right now in a parallel section. Michael Burtsev, they said, let's generalize this idea. Let's create like variations of how can we attend to. So they said, how do I go back? Yeah. They said, let's prepend several tokens to the input and say that these tokens are going to be attention sinks that always have our memory, like the CLS token. Then they said, does it need an external module to process it? That's the mem control transformer. Then they said, do we need to mix and match how the compressed attention flows into attention and how the attention flows into compressed attention? So they used several tricks, and all of them worked, and they essentially became the precursors for multi-head latent attention. So let's reach into that. So what is KV cache? I've been talking about KV cache. How are we doing on time? Okay. So as I told you, vanilla attention is an n-squared operation, and the KV cache says essentially let's have an external memory that we will use directly to recall all of the operations that we had priorly. So within the original depiction, we have the matrix Q, we have key and V, and we have to recompute key and value matrices every time. Every time. And now we say, what if for every t-1 token we save all the key and value matrices into an external memory, so we need to compute only a new token. And like this, we get that in order to get the new KV tokens, we just need to multiply one vector with one vector instead of one matrix with one matrix, so attention becomes linear. But we also have a linearly growing memory, which is not very nice. So KV cache memory grows linearly in terms of gigabytes. It's crazy, but however, our latency is also like very low compared to the quadratic attention. So there are very many ways to compress this KV cache without losing any meaningful information. One is called token eviction. One is called token eviction, so token level optimization, meaning that several tokens are not important for the final outcome, let's just remove them. We're not going to explicitly talk about methods because there is a whole topology on these things. I can talk like 2 hours on this and not be finished. There are model ways to finish this which are more important for us. So also token eviction is problematic because if we lose several tokens for hard tasks like long context reasoning, math reasoning, if we lose several like tokens, we might not be able to give a good outcome. So here comes multi-head latent attention, which essentially says, let's train an autoencoder between our layers right during pre-training, right during pre-training for fine-tuning, and essentially the model learns to compress in of itself. However, it's very costly, and we want to do it essentially on the fly for the models that do not have MLA. So we want MHA to turn into MLA for free. Can we do that? So there is this result mathematical Johnson-Linder-Strauss lemma that essentially says that for every random projection, we can have a projection that preserves the Euclidean and the angle distance between the points. However, we also get dimensionality reduction for free. So we use this idea very simply. We say, what if we compress our key and value matrices using this? Without any traininglessly. This has been seen before. It's like quite similar to memformer. Then we looked at keys and values, and we saw that keys and values have massively weird distributions compared to each other across layers, across different heads. So we have to decouple them. So essentially, this is the slide where it animates that we decouple them. This is not the interesting part anymore. So the interesting thing is that up until this point, we were operating on the assumption that we have to compress uniformly. Do we have 2 minutes or 20? 20? No, 2? 20? Jesus Christ, I'm running through this because I thought I was, okay. That's very nice, okay. Yeah, very nice. So, okay, the good thing is that now that we understand that we need to decouple the compressions of key and value matrices because they have different ranks, across layers they're different, and we need to decouple each layer compression as well for the very same purpose. That's why we create some 2 parameters per layer that in essence compress it and decompress it. we only keep the compressed cached version in our KV cache. So let's say we want to now train this theta LK and theta LV compressor matrices. Because up until this point I said, yeah, you just can use random Gaussian matrices and it will be good. Now, how can we train this? The very simple thing would be just sample a lot of KV cache samples and just train it as an autoencoder on a reconstruction loss. This already gives you quite literally state-of-the-art or very close to state-of-the-art on most of the tasks. One thing that you have to be very attentive to is the fact that you have to keep your compressor and decompressor decoupled, and your compressor, in essence, has to display columns that are orthogonal to each other. So the more linearly independent your columns are, the better. And you can have some conditions during training that facilitate it. But now came the good part. So up until this point, we did not ever have a method that was learning what budget per layer should we have to do KV cache compression. Explicitly learning, not searching for it, not like using a heuristic for it, but learning from data. So we said, why is, like, that doesn't seem very nice. And we said, what if we have a parameter beta LK and beta LV, where the sum of betas for each of the layers, across all of the layers, has to be the compression rate that you want to compress to. So we essentially add a Lagrangian condition on our betas. And we also have gammas, where we say, let's create like a compressor, a linear compressor for all intents and purposes. Now we decided the budget for it. The other question is, okay, let's say out of D we decided to use D half. Which D half should we use? The first D half, random D half? And essentially gamma is a simple categorical mask with zeros and ones that says which of the variables are important for this particular task. And we learn it using Gumbel softmax tricks and some straight-through estimation. So, uniform cache implies that we always keep safe the same dimensionality of matrices, but that's definitely not the best. A simple hack would be keep the cache of most recent tokens while compressing the rest. So we don't only want to compress on the fly always, we want to give the model a bit of a warm-up. So we want to say, just look at the 128 tokens, for example, without any type of compression, and only then we start to feel our compressed memory. So we have like a buffer that goes in front. To explain it better, essentially we can say we have a KV cache with a sequence and a buffer of sequence 128. So after decoding the 128th token, we say everything that comes after this is added to the buffer, and the last token is added to the KV cache. So we every 32 tokens after that, we put everything into KV cache. And the idea is that we have this pyramidal structure of buffers that even can be learnable. We can do hyperparameter search on this, obviously, but we can also learn what is the best structure to keep the KV cache in, what is the best pattern for this. But we didn't do this in this work, but that can be done. So the initial results tell us that if we want to do this without training, that doesn't work at all. Models get corrupted quite fast. We tested on Llama 3.18b instruct. We also tested models that are bigger. I don't think I have the graphs here, but the results are quite consistent in between each other. So then we said, okay, what if we just use the compressor to train? And that already works. So the decompressor is always the pseudo-inverse of the compressor, but the compressor is trained. That already works. That already gives us quite close to state-of-the-art ideas. And we also played around with what kind of a compressor-decompressor to use. So our compressor can be just one matrix, one linear matrix. It can be non-linear MLP. It can be a Gaussian mixture model. We tried to essentially do search. The idea is that it was very task-dependent for us, but the results are quite close to each other. So there wasn't a simple trend, so we decided to stick with linear matrices for compression and decompression. Indeed, it kind of turned out that decompressing non-linearly is not good in this particular case. And we see that for adaptive, where adaptive is the model where we learn the budget, we already get state-of-the-art, and this essentially shows how different from the original performance are we getting. And the lower the number, the better. So then we said, like, okay, let's understand how the buffered version of this would work. So like we added a buffer that's 128 tokens, to a buffer that's 256 tokens, longer and longer. And we saw that, yeah, adaptive essentially recovers on GSM8K, MEF500, and GPQA. The full accuracy of the original model without any compression, which is very nice for us. So we tried compressing it 2 times, 3 times, 4 times, up to now, like the recent results are on 64 times, and we only see variation of loss. So essentially, compared to the original model, we only lose up to 5%, which is very nice. But like we compress the memory by 64 times. Yeah. So, and the thing is, because we're using linear compression, like linear compressor and decompressor, the results can be very interpretable. Like we can directly multiply the compressor with the decompressor, and the ideal lossless case is we should get a diagonal of all ones, because like they cancel each other out. It's lossless. Obviously, that doesn't happen. This is the initialization stage, but after training, it gets better and progressively better. One more interesting thing that we found out is that there is a strong correlation between the layer depth and how much budget does it require. So earlier layers, actually, you cannot compress them much. Earlier layers, you have to like keep very consistent. Only you see that there's a cutoff there, because I said, like, if you don't compress at least by 10%, it's meaningless. You don't need to compress. That's why we have it like at 10% at the initial layers. But as you go deeper through the layers, there is some type of a like power scaling law, maybe polynomial, maybe exponential. We don't know yet. We didn't fit anything onto it. But there is definitely a law that says on the last layers, for a given task, even a very complex task, you can compress it by up to 80%, 90%, so x10 compression, which is very interesting to see. Now we have like scaling laws of what's a better way to compress LLMs per layer, or KV cache per layer. Yeah, the idea is to add more compressions. We already added 8, 16. We still are working on 32 and 64 to have like rigorous results. We need more benchmarks, of course, ruler, needle in a haystack to see it on a longer context. But overall, these are like the direction that we're currently taking for compression. Yeah, now I'm ready to answer questions.
Thank you, Erik, for your talk on the sparsity, even though being information dense. I'm wondering, I have a couple of questions, if you don't mind. The first one is actually, so you're trying to compress the KV cache, which essentially accelerate your inference, but you also benchmark on GSMK, which practically like single word or integer, right? So it's quite short. I understand that, okay, the KV cache is like technically smaller, and you retain the performance on GSMK, but would it be also interesting to, let's say, track it down the longer outputs for the benchmarks?
Yeah. That's why I said, like, we have evaluations going on Ruler 2, on NIA, needle in a haystack. So we have those coming up. We have some initial results that I can like offhandedly share. I just didn't prepare the graphs for those. So we know that on a needle on a haystack, it gets like perfect performance for like a context like up until 64K. But we didn't try like anymore. So I guess like the closest to like a good real world eval that's natural that we have is GPQA. So GPQA is already quite long context. You can get like up to 16K, 32K, but like we're able to recover the performance of the original model with up to 4x compression on that. With 8x compression, we have 2% loss around like that, but it's still acceptable for us. Like it's still within the like Pareto frontier that we want to pursue.
Yeah, sounds cool. And the question, but the first part of the talk was on the sparsity. So you actually mentioned that, okay, this is a post-training, but I was wondering, like, okay, without any training, but do you really think that, for example, the current, like, maybe modern frontier models attempts to actually mix the full attention layers with the partially sparse attention layers together actually helps your post-training experimentation or not really?
That's actually an amazing question. So I had to gloss it over at one point, but I thought I didn't have time. So the idea is that many architectures currently do, like NGPT from NVIDIA. There is like variations of hybrid architectures that use full attention plus sliding window attention.
Yes,
So what we saw in our experimentations on average is that there is always some type of a loss on a task. But usually the task should be one of the tasks, like a natural long context task, like AIME, like like HLE, like some very complex task where windowed attention essentially loses the information of a token that you need to attend to. But outside of that, if we're just talking about average model serving for creative purposes, it's quite decent.
Okay,
Yep.
I see. Thanks.
Thank you for presentation. It was very hard to hear from here because we hear from multiple
Yeah,
echoes.
I can imagine. I'm sorry about that.
But here's the question. So compared compressed LLM and SLM, small
Compressed
language
LLM
model, and small language models,
yeah.
what would be advantages or disadvantages? Because like literally compressing methods are pretty good nowadays. Maybe there is no need for SLMs, and I know NVIDIA is pushing them. It's interesting.
So that's a good point. So one thing is that we found that just sparsifying attention with strict patterns, like on the paper that I presented, we just saw that, yeah, just making the model bigger and more compressed usually works better. But that's only for training free sparsification. That's a very specific result. So I'm quite sure that if you actually train your models to choose the patterns dynamically or learn the patterns dynamically or like mix and batch, like do some type of neural architecture search, which we do at NVIDIA, like you're bound to get results that are not are overlapping on the Pareto frontier. So essentially, you can and will possibly get a small language model that is dense, that has like much more floating point operations per second, that's able to throughput much more floating point operations per second. That is better than some very compressed big model. So that is definitely a possibility with learned attention patterns, with learned sparsification. But we just don't know like what's the scaling laws of those are. At least like I haven't seen a paper on that. Maybe someone has already created those, but at least not me.
Thank you, Erik. I just wanted to add to the previous point, there's actually some research showing that creating a bigger model, training a bigger one, and then compressing into a smaller one actually gives better performance and quality than training a smaller one from scratch to match the one that is actually research.
If you're talking about knowledge distillation,
yes,
yeah. Like in knowledge distillation words, that's definitely a phenomenon.
Yeah.
Definitely. What I was talking about is, like, let's say we just have two pre-trained checkpoints, one is bigger, one is smaller, and we don't try to distill one into another. We just say, yeah, let's compress the smaller one, let's just leave the smaller one and compress the bigger one. That's the only thing I was talking about. But in knowledge distillation, definitely that's a phenomenon.
Yeah, sure. So you could compress it with different methods, and as long as you add distillation on top, you actually recover most of the quality.
Yeah.
So,
I think though we have seen like quite a big amount of math benchmarks and physics benchmarks that are solved in this way. Yeah. Okay. I guess if there are no more questions, we can just hang around.